Welcome back to part 3 of section 5.3, linear independence. So we've talked about how to check if arrows are linearly independent, but we saw that other things are vector spaces, including polynomials of degree at most 2 with real coefficients. And so what I want to do is have you check if x plus 1, x squared minus 1, and x squared plus x are linearly independent or not. Well, let's do this one together. So we're going to do C1 times x plus 1 plus C2 times x squared minus 1 plus C3 times x squared plus x. And we want to see if that's equal to the 0 vector. Under standard operations, the 0 vector in P2 is 0x squared plus 0x plus 0. So if we look at this together, it's going to create for us a linear system. And we'd have 0 C1 x squared plus 1 C2 x squared plus 1 C3 x squared equals 0 x squared. So that first row would be 0, 1, 1, 0. For the x coefficient, we'll have C1 plus 0 C2 plus C3 equals 0. So 1 C1 plus 0 C2 plus 1 C3 equals 0. And lastly, we'll have 1, negative 1, 0, and 0. If we take this matrix and put them into our calculator and put them in reduced row echelon form, we will get the following. Again, we see that we have two non-zero equations in three unknowns. Therefore, we're going to need a parameter. So if we let C3 equal t, then C2 would equal negative t, and C1 would equal negative t. If we let t equal 1, we'll just call it that. Then we've got negative times x plus 1 minus x squared minus 1 plus x squared plus x, and you'll notice that that's 0x squared plus 0x plus 0, or the 0 vector. Okay. And we could use that then to solve for any one of these guys in terms of the others, so that because we know that this set of vectors is, in fact, linearly dependent. Okay. So, for example, I could solve for x plus 1. Since he's negative, I'm just going to move him to the other side. So x plus 1 would equal negative x squared minus 1 vector plus x squared plus x vector. So you could see that anything that we could make with x plus 1 could have already been made with x squared minus 1 and x squared plus x. Also, we could solve for the x squared minus 1 guy, and he would be negative x plus 1 plus x squared plus x. And finally, we could even solve for x squared plus x, and that would be the x plus 1 vector plus the x squared minus 1 vector. So you can see again that we've shown that this set of vectors is linearly dependent, and in fact, any one of the three could be thought of as the unnecessary vector that we could throw out and still not hurt our span. Now, can you think of a nice set of vectors in P2 that are linearly independent and would span? I'm going to pause it and let you do that while you list them. Okay. I came up with x squared, x, and 1, because if I want to make any vector u being ax squared plus bx plus c, I can write u as a times the x squared vector plus b times the x vector plus c times the 1 vector. And since they're all different powers, they've got to be linearly independent. We could check that by doing c1x squared plus c2x plus c3 times 1 is equal to 0x squared plus 0x plus 0. But you can see that then that has to force c1 to be the same as c2. All of these guys have to be 0. So we've shown that they span all of polynomials of degree at most 2, and they're linearly independent. Now, these guys are actually pretty spiffy, because if we look at these guys, this x squared could be thought of as 1x squared plus 0x plus 0, which, if we keep things in the right order, could be thought of as the vector 1, 0, 0. Similarly, the vector x in P2 is 0x squared plus 1x plus 0, which could be thought of as the vector 0, 1, 0. And unsurprisingly, 1 is 0x squared plus 0x plus 1, which is very much like the vector 0, 0, 1. And you can see how these are just like the I, j, and k vectors that we've played with in R3. In fact, you could take a look at these guys up here. The reason I left a little bit of space is you could think of this as an analogous to the vector 0, 1, 1, as long as we remember that the first coefficient, or the first component, is the coefficient of the x squared, the second component is the coefficient of the x, and the third component is the constant term. And similarly, this would be 1, 0, negative 1, and finally 1, 1, 0. Okay. All right. Hope that's made sense. Let's move on to our next page. Okay. Professor Boggio loves matrices. So what I want you to do is check to see if these matrices, which are in the M22 vector space, matrices that are 2 by 2 with real coefficients, are linearly independent or not. So I'm going to let you go ahead and give that a try, and then we'll come back together and see what you were able to come up with. Okay, so hopefully you set up the equation here, checking for linear independence, which leads us to this matrix, which when we RREF gives me this form right here, which tells me that I have a parameter. So I have infinitely many non-zero solutions. So if I let t equal 1, then I've got negative 1 times 1, 1, 0, 0 plus 1, 0, 1, 0 minus 0, 0, 1, 1 plus 0, 1, 0, 1. That would make the 0 vector. So these vectors are linearly dependent, and using this equation, I could solve for any one of these vectors in terms of the other guys, showing that it would be unnecessary. It wouldn't contribute anything to what we could have reached with the other guys. So can you think of a nice set of vectors that are linearly independent and span all of M22? List them. Well, probably not too surprising. But this set of vectors would span all of M22, because if I wanted to make some matrix A, B, C, D, I would use A of the first one plus B of the second one plus C of the third one and plus D of the last one. And if I create a matrix out of this, it'll just be the identity matrix. So if I try to do a constant multiple of the first one plus some other constant multiple of the second one, so I set up the definition of linear independence and set that equal to the 0 vector, which under standard operations would be the 0, 0 matrix. The only solution there would have to be all of the C's are 0. So it is both linearly independent and it spans something very important that we will talk about next section. So let's pause right there and we'll get to our next video.